All right, so exponential functions applications. There's really two different types, and we're going to do them both right now. There's exponential growth and exponential decay. So we're going to do it all in one big note here. When you're looking at this, so typical example is a bacteria colony. When you're looking at 90% of exponential growth, the first example they look at is always bacteria. So if we had a bacteria colony doubling every minute, and there's 10 bacteria at the start. So we're going to have 10, and then we're doubling it every minute for 9 minutes. So times 2, times 2, times 2, times 2, times 2, times 2, times 2. That's what, 7, 8, 9. Okay, if we look at this is really 10 times 2 to the 9. Looks like an A. Okay, and 10 times 2 to the 9. So 2 to the 9 is going to give me 512 times 10 is 500 or 5,000. Let's do it like that. 120. Okay. Now, when we're looking at this, the general equation for an exponential growth or decay is f at x is the final value A is our initial value or starting value. B is the growth if it's greater than 1, or decay if it's less than 1. And then X is the number of growth or decay periods. All right. Important notes. So if growth or decay is given as a percent, then the base of the equation can be added or subtracted to 1, and we're always going to change that percent to a decimal. So for example, if we had a growth of like 4%, we would add that to 1, it would be 1.04, and that would be our growth. Okay, also the units for growth and decay rate and for the number of growth or decay periods must be the same. So if we were growing if we were doubling every minute, we couldn't have our time be in hours. That just wouldn't make sense. Okay, so first example. So growth problems. In 1996, Alberta had a population of 35,000 people. Recently, it experienced a large population growth due to the oil deposits. More recently, it's lost that, but I didn't change the example. Alberta's population has grown at a rate annually of 8%. The algebraic model for this case is. Okay, so the first thing we need to look at is what's the initial population. So our initial number here is 35,000. Okay, our growth rate, or our B value, we're going to have is 1.08. I'm going to change 8% to a decimal, which is 0.08. I'm going to add it to 1. So then the equation we're going to have, if we were looking at population, typically you would have P at X. You could write it as F at X. It's not a big deal. So P at X equals 35,000. And then we've got 1.08. And then we've really got to just look back to the question. It's an annual growth rate. So that just means we're going to have X, and X is going to be given in years. So use this to determine the current population. Well, we're going to have P at, now we're in 2020. So 2020 minus 1996, because that's going to give us our original year, it's going to be 24 years. So we're going to have 35,000 times 1.08. And if this model held true, and I'm going to write across here just because I've run out of room, if this model held true, we'd be able to use this equation. Now, sometimes models don't hold true or they break down after a while, but for all of our examples, we're going to just assume that they hold true and they don't change. So this is saying that Alberta's population now is 941. Okay, 221,941 people. All right. And how long will it take for our population to triple? Now, there's kind of a couple different ways we can go about doing this. I'm going to say two. The first would just be to take 35,000 and times it by 3. So we're going to have 105,000 equals 35,000. And then we've got 1.08 to the x. The other way would just be to start with a 3 here and assume that we have a population of 1. So then we're just going to have 1.08 to the x. Now, both of these questions are exactly the same. They're set up the exact same way. But just because we've made our triple in rate, or the time that it's taken to triple, if I had 1 person or if I had 1,000,000 people, the time, if I'm growing it at 8% per year, is going to be the exact same to triple. Okay, so here, because we're going to have to divide this 35,000 over, we're going to get 3 equals 1.08 to the x, and it's just taking a step out. So then we're going to have x equals the log of 3 divided by the log of 1.08. And again, this goes back to our note from before. And then the log of 3 divided by the log of 1.08 is equal to 14.3 approximately. So therefore, in approximately 14.3 years. All right. Next one. So bacteria culture starts with 3 bacteria, doubles every 20 minutes. So these ones are a little bit harder. So we're going to have f at x again, or we could have p at x. It doesn't really matter. We've got our initial rate. We've got our doubling. Now here, though, we're doubling every 20 minutes. So that means that when we have our x, we have to have 20 x's to make 1 doubling period. So what we do is we do x over 20, because then after 20 minutes, we'd put in x as minutes, and then 20 over 20 would be 1 doubling period. All right, so here we've got f at 90 equals 3 times. I like to put brackets in here just so that I don't mess up my exponents. We need to do our exponent first and then multiply it through. So we're going to do 2 to the 4.5, or 2 to the 90 over 20. So 2 to the 4.5 times 3. So we're going to get 67.88. Now, depending on the book you're looking at, you should always round down with population because you can't have a decimal of a person. Here we'll do 68.9, therefore, or sorry, 67.9. So therefore, 67 bacteria. Okay. Depending on the book you're looking at, they all kind of do it differently. I say always round down when you're using population. So how many bacteria after 3 hours? Well, 3 hours equals 180 minutes. And that's what we're talking about here. So we're going to have f at 180 equals, oh, that's a terrible 8. Let's connect that. 3 times 2 to the 180 over 20, which is just 2 to the 9. So 2 to the 9 gives us 512 times 3 gives us 1,536 exactly. And therefore 1,536. So another culture had the same doubling time after 2 hours, had grown to 704. What was the original size? So in this case, we're just using the same formula, but we know what f at x is, and we don't know what our original value is. So we're going to have 704 equals, we'll call it A. We've got 2, and what do we have? 2 hours. So 2 hours is 120 minutes. 120 over 20. So 704 equals A times, and 120 over 20 is just going to give us what? 10? So 2 to the 10 is, I'm wrong here. 120 over 20 is 6. 2 to the 6 is 64. That's going to give us a better number here. And then A, it's just 704 divided by 64, which is 11. Therefore, 11 to start. All right, last one. So this is a money one. In 1990, a sum of $1,000 is invested at some rate per year for 15 years. What is the annual growth rate of this investment if the total is going to be $5,473? So again, what we're looking at here is an annual growth rate. So what we have to have is we've got we'll write down this. All right, so now we've got our final value is $5,473.57. Our initial value is 1,000. We've got B to the 15. Okay, so we're going to divide that 1,000 over. So we've got 5473.57 divided by 1,000. So that's going to give us 5.47357. And I don't want to round until the very end. I've got B to the 15 because it's 15 years. Now, to get rid of that 15, I have to take the 15th root. Okay, so now on both sides, I'm going to write this in. We're taking the 15th root, or putting it to the exponent, 1 over 15. So then that means B equals to the 1 divided by 15, 1.12 and a bunch of zeros. So what we actually have there is we have to subtract the 1 away. So our growth rate equals 1.12 minus 1. And then we're going to times that whole thing by 100%. So really, this is 12%. Okay, so therefore, 12% is the growth rate. All right, so looking into this, we're not going to do this question. This is another growth question, and I want to start with decay. So we'll skip that. If you want to do it, you can do this question another time. But let's get into decay. I want to just do a couple. They're very, very similar. A new car depreciates at 18% per year after it's purchased. So what's the depreciation rate? So what this is asking for is our B value. So really, if we have 1 as our normal, we would add 18% to 1. For depreciation, we're going to subtract. So, or you can do 100 minus 18, and you'd get 82. And either way, you're going to change it to 0.82. So then we want to write an equation. We're going to have f at x equals, we've got 24,000. That's the initial price of the car, times 0.82, and it's per year. So we'll just call it x. How much is it 6 months after we buy it? Well, we've got f at x, or f at 6, is 24,000, is 0.82 to the 6 equals, so 0.82 to the exponent 6 times 24,000. So after 6 years, it's going to be worth $7,296.16. So therefore, we have that price. Use the equation to determine the value after 30 months. Well, we need to change 30 months into years. So T equals 30 divided by 12. Now 30 divided by 12 is going to give us 2.5. So then we're just going to do f at 2.5 equals, so we've got 24,000, 0.82 to the 2.5 equals, so 0.82 to the 2.5 times 24,000 is going to give us $14,613.22. Therefore, that's our answer. Now I'm going to do one more kind of question here. What if we wanted to find out, so again, this was our equation, so we've got f of x equals 24,000 times 0.82 to the x. And what if I wanted to find out when this was worth $0, so when we had no more price? So what we'd have to look at is we would put f of x as 0. So 24,000, or actually, let's do it this way. If I put 0, we're not going to get an answer, but let's put 0.01. Let's find out when it's worth 1 penny. Okay, so when it's worth essentially nothing. And then after that, we're going to say anything after this time. So we're going to do 0.01 divided by 24,000. And we're going to get a really small number. 1, 2, 3, 4, 5, 6, 4, 1, and then a bunch of sixes. Equals 0.82 to the x. And we're going to log all of those numbers. So what is that? We'll call it 4.2 times 10 to the negative 7. Now I'm not actually doing that. I left that number in my calculator. It's just easier to write it that way. So then we're going to log that divided by the log of 0.82, and 74 years later, or 74.028. So therefore, the car is worthless after 74 years. All right, so last question here. We've got a 200 gram sample of plutonium. So we've got a half-life. This means that every 138 days it goes down to half. So our decay rate here is 0.5 because we have a half-life. Our equation, so we'll call it P at x, I guess, this time. Doesn't really matter. Actually, let's just call it F at x. We've been using F for everything. So F at x equals, our sample is 200 grams. Okay, that's important. This is not. That's just the name of the product. Okay, a lot of people confuse that. Now we've got x, and we've got to go over 138. This is the same reasoning that we had before when it took 20 minutes for something to double. It takes 138 days for this to cut in half. So when x is equal to 138 days, we've multiplied by a half once. When it's equal to 2 times 138, we've multiplied by a half twice. Okay, we need to have it x over 138. Determine the mass after 5 years. Well, 5 years, we're going to do 365 times 5. We're not having any leap years here. So x equals 365 days in a year times 5, which is 1,825. So then f at 1,825 equals 200 times that same value, 0.5 times 825 over 138. Okay, this comes down to being pretty good with your calculator. So we're going to have 0.5 to the exponent bracket 1825 divided by 138 equals times 200. So you should get 0.02, we'll call it 09. Okay, therefore there are 0.0209, what is it, milligrams or grams? Grams remaining. Okay. Now, if we wanted to kind of look at this, let's just make sure. 1825 divided by 138 means we've had 13 half-lives. Okay, 13.22. Okay, half of 200 is 100. Half of that is 50. Half of that is 25. Half of that is 12.5. We're getting down to 6.5, and we've only gone through 5 times. Okay, so it's probably pretty close to our answer. How long does this sample take to get to 110 grams? Okay, we know our final value then is 110. We know our initial value, again, was 200. We've got 0.5 to the x over 138. Okay, now this is the nice thing about using the log method. We're going to do 110 divided by 200. We're going to get 0.55 equals 0.5 to the x over 138. Now we're going to have x over 138 equals the log of 0.55 over the log of 0.5 we're going to get 0.86, but then we're going to times it by 138. And it's going to give us 119. So therefore, 119.02. Therefore, there will be 110 grams left after 119 days. Okay.